And in our sample proportions, I'm going to launch an applet on the computer, and I'm not really sure if this applet records what's going on the screen. I know it does for the active board, but I'm not sure about the applet, whether it'll record it or not. I think it will, but I'm not sure. But the web address is up there, so if you ever want to go back and look at it again, you can go into our notes, take a look at it, or as you're watching the video. And so it's called rossmanchance.com, and the one I'm going to use is the Reese's Pieces one. So imagine that you have a very large candy machine filled with orange, brown, and yellow candies. And when you put money in, the machine dispenses a sample. We're going to use this Java applet to investigate sample-to-sample variability in the proportion of orange candies dispensed by this machine. So I'm going to launch this Reese's Pieces applet, and we're going to notice the population proportion is going to be set to 0.45, already in the machine. And then they call that pi instead of p. I don't really know why. So here it is. Nope, there it's not. So here it is. And then it says we're going to draw some samples. So you see here where it says pi, that's really p. Okay? And it says in here that we're going to do a sample size of 25. So down below you'll see sample size of 25. And we're going to do a random sample. So I scroll down and I draw my sample. And the machine is dispensing all these candies. Bless you. And what you'll see is that when you do this, we get a p-hat, or proportion of this sample, 48, or 48% of the candies were orange. So now, in our first sample, back in our notes, I notice that my first sample technical difficulties. My first sample had a p-hat of, what did I say, 48? 48.48. Now, if you look online at the notes, Bart's did this, and he doesn't have the same sample, and we're never going to get the same samples because it's random. So you look at this thing here, and is this the population proportion? No. No. It's off by 0.03. So now I'm going to go back into the machine and I'm going to draw 9 more times so that we have a total of 10 samples. So I go back to the machine and I'm going to do 9 more samples. And as I look at my samples being drawn, you'll see the dot plot show up and place the proportion of all these samples. And if you recall yesterday when we were talking about this, we were drawing samples of, for example, size 20, and we draw a couple hundred of them, and we see a dot plot of the proportion of each of the samples. And over time, you'll notice that the distribution of the proportions is approximately normal. Because any one sample could be extremely different, like when we talk about heads and tails in a coin. But when you look at the dot plot of all of the samples that you draw, then you see something that's a little more normal. So now when I look at this, I start to notice some of the things that are going on here. For example, it looks like my proportions went from, I don't know, maybe 0.32 to 0.6 for my samples. So let me just go back to our notes, see what they asked there. 0.32, 0.6. Okay, so I notice in the next one that my spread is p hat equals, it looked like 0.32 to me, to maybe p hat equals 0.6. So there's a spread there. I don't know if down below, do they talk about anything else in there? Oh, they also gave me in this applet the mean and the standard deviation. So somebody could write those two down so that when I flip back to my whiteboard, you can tell me what they are. The mean is 0.476, and the standard deviation is 0.085. Okay, so now I'm going to go back to my whiteboard. So I could also write that down. So I had my mean of my sample proportion was 0.476?
Yeah.
0.476. And the standard deviation of my sample was 0.085.
Yeah.
Okay, so notice how these things over time in the next step here, when I do a lot more sampling, that might change. So let's go back to the machine one more time. And in this machine, I'm going to do a total of 400 samples. So I need 390 more samples. And this might take a while, so I'm just going to pause the recorder. So now I look at this, and as I look at this dot plot of my 400 total samples, let's talk about the shape. What do you think about the shape? It's approximately normal. Fairly symmetric, right? What about the center?
Around 4 or 5.
The mean is 0.455. That's much closer to 0.45, which we were supposed to get. Standard deviation is 0.104. The range looks like it goes from, ooh, there's one way down here. You see that one?
Outlier.
That probably is an outlier. So we have all the way from like maybe 0.12 to 0.68 with a possible outlier at 0.12. So I'm going to write all this stuff down in our packet. Thanks for the animate thing. So first of all, the shape looks approximately normal. It's symmetric for the most part. The spread was from, it looked like p hat of 0.12 to p hat of 0.68, I thought, looking at it. Again, this will be different than what you see online notes because Mr. Bartz did this and you got something different, I think. What else do we talk about? We had a mu of the p hat was 0.455, and our standard deviation of the p hat turned out to be 0.104. Four, making bigger. And it looked like the p hat of 0.12 could be an outlier. And what this simulation was trying to show you is that when you take one sample proportion, then your results might not be what you'd expect from the population. But over time, if everybody takes a sample like that, then what's going to end up happening is you'll see a distribution that mimics what you would expect to see, with the mean close to the population mean, and the same with the standard deviation. So that's kind of the big idea. Lots of samples. Okay, so now what I'm going to do is I'm going to reset the machine, and I'm going to make my n be 50 instead of 25, and we're going to take 400 samples. So I go to the machine, and I want my n, my sample size, to be 50. Okay, let's reset it to clear everything. So 50. And then I'm going to take, how many samples?
400.
400, thank you. 400 samples. The animate's off. Boom. Okay, so first of all, when we're doing this, one thing that happened was the sample size increase. What does sample size increase do for us? One of the first things that pops in your head.
Decrease variability.
Decreases variability. That's huge. That's the first thing you should always think about when you talk about the bigger sample size. And then second of all, we drew more samples, which also, again, probably would decrease variability and show you an approximately normal curve. So as we look at this picture, you can see that our graph has tightened up. So instead of going from 0.12, notice that the smallest looks like it's at 0.26 maybe. And the biggest looks like maybe 0.64. So we've tightened up because of our sample size and the number of samples. So now I'm going to go back to our notes and answer these questions. First question said, what about the shape? So the shape is symmetric, again, or we say approximately normal, which sometimes people have talked about as a bell curve, but we don't talk about it that way necessarily specifically. Did anybody catch the mu?
0.454.
454?
Yep. Yeah.
Okay, thank you. So the mu of our sample proportion was equal to 0.454, and I didn't catch the standard deviation either. All right, so I'll go back and look really quick here. The standard deviation, 0.066. Much smaller. Notice how much that decreased compared to the 0.10. The spread in ours was p hat equal to 0.26 to p hat equal to 0.64. And we noticed, and probably the most important thing, is that our variability decreases with the increased sample size. That's huge. As I look at changing it to 0.15 for the P, sample size of 25, drawing 400 samples, let's see what happens. So my P is different. Did it really change anything?